Okay, let's put a cone around a sphere. We want to show that the least possible volume of a right circular cone circumscribed about a sphere is twice the volume of the sphere. Okay, and here's an illustration over here. This is like a vertical center cross section of the cone and the sphere. So say this is the sphere here. Here's the cone on the outside. The radius of the sphere is little r, and that's going to be a constant here because our sphere is a particular sphere that we're working with. We're looking at a whole bunch of different cones, so we'll call the radius of the cone big R and the height little h, and of course those are variables. And we need to get the volume of the cone as a function of a single variable, and then use calculus to minimize that function. So let's get started by writing down the volume formula for the cone. It's V equals 1/3 pi r squared times h. But we need this as a function of a single variable. So what we'll do is we'll use this picture over here, and notice I've already formed some triangles. Here's this little red triangle here, and this bigger yellow triangle outside here. And both of those, they share this angle up here, and they each have a 90-degree angle. So that means their third angles have to be equal as well. See these two triangles that I'm talking about, this red one right here, and then the big yellow one that's kind of sitting inside, those are similar triangles. And I've labeled the sides of these triangles. So this distance here, that's the hypotenuse of the smaller red triangle, that's h minus r. This is this distance here is little r, the radius of the sphere. And of course, the reason this is a 90-degree angle is because this is a radial line and a tangent line, and those types of lines are always perpendicular to each other. And then the Pythagorean theorem and some simplification via algebra gives me that this leg of the small red triangle has length square root of h squared minus 2rh. And then for the bigger triangle, of course, this distance here is big R, and this distance here is h. And if you're wondering where this h minus r came from up here, well, that's this distance here, which is the whole h, and then minus this r part here, so that's where we got the h minus r. Okay, so using our similar triangles, we can take the ratios of the legs on the red triangle. We can take this r over the square root of h squared minus 2rh, and set that equal to, working with the bigger triangle, we take the ratio of its corresponding legs, and we get big R over h. Okay, so that gives us this equation here, which we can get r squared from, and then put that r squared in over here to get our volume as a function of a single variable, which is what we want. So you just multiply both sides of this equation by h to get big R, and then after that square both sides, and we'll have big R squared. So let's go ahead and do those two steps all in one. And we get big R squared is r squared h squared divided by h squared minus 2rh. That can be simplified. I see a common factor of h. Divide top and bottom by h. We get r squared h divided by h minus 2r. Okay, so r squared is equal to this quantity here. Okay, so now we can take our volume function for our cone and put that version of r squared in. We'll have something to work with here. So when we do that, we get v is pi over 3, and then times our big R squared times h. So just times this guy times h. Okay, so that's going to give us times r squared h squared divided by h minus 2r. Okay, and that is our volume function as the function of the single variable h, because little r is a constant. Now the domain of this function, if we look at this carefully, we know we don't want either r or h to be 0, and h obviously has to be bigger than 2r. Otherwise you wouldn't be able to put this sphere inside the cone like this. Okay, so the domain is h is bigger than 2r. Let's just go ahead and take the derivative, find our v prime, and see what happens from there. We get v prime is pi over 3 times, now we need our quotient rule, so we need bottom h minus 2r times the derivative of the top, which is 2r squared h, and then minus the top, r squared h squared, times the derivative of the bottom, but the derivative of the bottom is 1, and then over our h minus 2r squared. And of course we want to set that equal to 0 to find our critical numbers. Well, 0 or undefined, but it's never going to be undefined because h minus 2r will never be 0 because h is bigger than 2r. And the only thing that makes it 0 is the numerator to be 0. So what we need to do is set the numerator equal to 0. And in the process of doing that, let's simplify this numerator as well. We need this numerator to be 0. When we multiply this part out, we're going to get 2r squared h squared. Okay, so 2r squared h squared. Okay, and then from multiplying these two guys, we're going to get a minus 4 r cubed h. See, 2r squared h squared, okay, and then minus 4 r cubed h, and then minus r squared h squared. We want that to be 0. Obviously, we can combine this term with this term to get a single r squared h squared. So we get r squared h squared minus 4 r cubed h equals 0. Well, we can factor r squared h out, and we get r squared h times h minus 4r equals 0, and that gives us that h is equal to 4r. Okay, so we have the single critical number, h equals 4r, and we're working with a function of a single variable. So if we can show that there's a local minimum there at h equals 4r, then the absolute min will be there as well. Well, if you come back up here to the derivative, the v prime, pi over 3 is positive, h minus 2r squared is positive. What affects the sign of this derivative is just this numerator, which down here we set equal to 0. So in fact, here's the numerator right here. Here it is again right here. So here's our numerator. R squared h is positive, and when h is smaller than 4r, this h minus 4r is negative, which makes the derivative negative, and that means the volume function is decreasing, coming up to 4r from the left. And then when h gets bigger than 4r, h minus 4r will be positive, and that will make the derivative positive, so your volume function will be increasing as you leave 4r going off to the right. So that means we do indeed have the min at 4r. So now all we have to do is show that the volume of the cone when h is 4r is twice the volume of the sphere. And we can do that by looking at the ratio, the volume of the cone to the volume of the sphere. Okay, so let's go ahead and do that. Now remember, we're doing this when h is 4r. So volume of the cone will be 1/3 pi big R squared times h, but that's 4 little r. And then divided by the volume of the sphere, which is 4/3 pi little r cubed. Okay, let's simplify that. The pi's cancel. 4's cancel. The 1/3's cancel. We've got, after all said and done, we just get big R squared over little r squared. But big R squared is this guy right here. So we'll put that in. That gives us r squared times h over h minus 2r. But again, remember we're doing this when h is 4r. Okay, so when h is 4r, in this numerator here, we get 4r cubed. For r cubed over h minus 2r. I just realized I still have to divide by this r squared here, so I need an r squared right there. I also need it over here. Okay, so now we'll continue our simplification here. This is going to give us 4r cubed. Then over, there's our r squared. Remember, we're doing this when h is 4r, so I should have put that in right here, but I didn't, so I'm going to do it now. So when h is 4r, h minus 2r is 2r. So we've got 2r here. And that gives us 4r cubed over 2r cubed, which is 2. So we're done. We've shown that the volume of the cone is twice the volume of the sphere. Thanks for watching.